Again, good morning and welcome to Physics 4B. We did not finish chapter 30 last time around, so we still need to finish chapter 30. So instead of doing problems right away on it, because of the fact that chapter 30 ties into chapter 31 in terms of the circuit, really, the main component of these two chapters is the RLC components, namely a resistor, an inductor, and a capacitor. And we're going to do them in series. So the first part that we've been dealing with, okay, that's fine. The first part that we've been dealing with is the fact that I put them together, okay, and we put them under basically we can put them under no current whatsoever. We can put them basically connected together, and we put a charge, for example, in the capacitor. We know that the charge, since you connect the circuit, is going to start to discharge. So it's going to find a way to start to discharge. As it does, it's going to go to the resistor. The resistor will basically dissipate the current through the ohmic heating, namely Ri squared is the power with which we get rid of current of energy in a resistor. But then it's going to go through an inductor. The inductor now will keep on pushing it because it doesn't like the current to change. Once the capacitor runs out of energy, once the capacitor runs out of charge, in this case, there is energy would be stored in the form of a current inside an inductor, which would keep on pushing it, rebuilding, if you wish, the charge in the opposite direction in the capacitor. During that cycle, it's actually the energy is being drained off of the inductor. Now, at some point, the inductor will run out of energy, in which case now you have energy inside the capacitor. The capacitor will try to push it in the opposite direction. In doing so, it's going to build up a current in the inductor, but then the resistor is there to spoil the fun because it's going to dissipate that energy still. Whichever way the current is flowing, you will always have energy dissipated in the resistor in the form of Ri squared, where I is a resistance times the current squared. And that is the rate at which power is being dissipated inside the resistor, so it's going to waste more energy in the second stage. So during this stage, now the capacitor is pushing in a current in the opposite direction, trying to get rid of it because it wants to cancel all of its charge, but then energy is being now converted into the inductor into a form of a current. So at that point, once the capacitor runs out of energy, runs out of a charge, namely, then there will be a big current running through the inductor, in which case the inductor pushes the current through because it doesn't want current to change. So the process basically reverses, and now I'm building charge inside the capacitor in the opposite direction. Meanwhile, you have that resistor sitting in there wasting energy in the whole process. In this situation, the resistance is not high enough. There is a resistance, but it's not high enough. So what's going on in this case, you have oscillation of the current going back and forth, but with damping. The damping in here is in the form of how much energy is being lost to the capacitor, to the resistor inside the resistor. The first cases that we saw so far actually are the two cases where R is huge, R is big. The first case when R is so dominant that it doesn't even allow the first stage to happen. In a sense that the current will be completely wasted in the resistor and does not allow for the current to build up strong enough to have it in the inductor to even change it, to keep it going. So basically, in that case, all of the energy that was stored in the capacitor was gone in the form of heat that was wasted in the resistor. So that was a case of the overly damped circuit. In other words, the resistance is dominant. And the second case that is actually of a critical damping, R has this unique value so that the square root in the solution that we found is exactly 0. We call this one critical damping because of that condition, because we have to find the solution. And that too is actually exponentially decaying, but not as fast as the first one. So it decays exponentially, but not as fast. But it still goes to 0, again, because of the resistor. The third scenario that we didn't finish last time around is the one that I described in the intro, namely the fact that the current, let's say, for example, you have this much charge in the capacitor. So the charge starts to go down a little and changes direction as the current is being pushed back and forth between the inductor and the capacitor until we run out of completely charged. Because during each cycle, there is that still resistor in there that is killing the current. So it's going to kill it, but not without both of them having say-so about it. In other words, there is an oscillation, and it's dampened oscillation. So it's not the pure oscillation when it goes back and forth forever. No, it's an oscillation that goes back and forth and starts, its amplitude starts to go less and less until you run out of it. So this is the case that we did not explore. So let me finish that. And then, if you wish, you can put a power supply. The power supply usually is really not needed in this situation, in this format, because all that happen is there will be, because of the power supply, okay, there will be a current that is going to be pushed. There will be a charge that is going to be oscillating, pushed. There will be everything, but there will be a transient, basically, where there will be an oscillation around the new voltage, if you wish, around the new current, or now the new charge. So there will be a rise, but then oscillations because of the fact that we have the square root in there. And then after that, it becomes steady. This case is not really of interest, honestly. The case of a big interest is the case when the power supply is actually changing with current, like an AC circuit. Like, for example, if I build an AC circuit and go and plug it into the wall, then in this situation, and actually have is a circuit that is driven by a power supply that is changing back and forth. That can lead to interesting phenomenon. One of them is resonance. And that is the topic of chapter 31. So what I'm going to do now is finish chapter 30, go to chapter 31, finish chapter 31. I don't know if we're going to finish it today because it's a huge topic, honestly, too. But then once we do that, then we're going to do problems that are a combination of the two chapters. We will have chapter 32, which is the last chapter by itself. Chapter 32 is a completely different setup. Okay, what you have in there is the following scenario. You are in empty space, far away from everything else. Okay, there is no charges in empty space, and there are no currents in empty space. In other words, there is no source for the electric field. There is no source for the magnetic field, and you are away from them. This is called free space. Now, we are in free space, but there is somehow an electric field and a magnetic field that came to it, non-zero values in there. So they're going to propagate through the empty space. This leads to electromagnetic waves. They carry with them an energy, and that energy ties up to the concept that I introduced way back, namely 1/2 of epsilon naught times E squared for the electric field, and 1/2 of B squared divided by mu naught, which is for the magnetic field. That too is actually what the electromagnetic energy is going to be like. This leads to a concept which is very, very critical in telecommunications, and that is Poynting vector. Poynting vector is very, very extremely important. So in other words, you have an oscillator somewhere, or you have a source of light somewhere, like a star or planet, or a star, I'm sorry, or the sun or something that generated those fields. And you are in between now, far away from the source. You don't have any electric fields, electric charges. You don't have any currents. What's going on? So that is the problem. So it's used in telecommunications and sending and receiving signals and doing all kinds of things with it. But that's chapter 32, and we will be done with the course. Sounds fun?
Sounds like a plan.
Okay. Yes. Okay. So let me get into chapter 30. So this is basically where we left off last time. Let me move this a little closer here. So basically, we looked at this equation. Okay, this is differential equation. If you're going to take dpq, this is actually the step into the problem. Actually, you do first order, and then you do the second order. Most of the times, your math teacher will remind you of the problems from physics. Okay. That this is actually, they will use this examples from physics. Then we said, okay, let's look for a solution of this behavior. So that constant doesn't matter. So it's going to get out anyway with the exponential and everything else. So in other words, we converted the problem from being a purely mathematical problem, a purely physical problem with the differential equations and things like that to an algebraic equation, because this is the quadratic equation. Which alpha makes this equation 0, basically? That's what you're asking. Because once you find that alpha, you found the solution that you're looking for. So we said, okay, we have to solve this quadratic equation. When we solved it, there are two roots for the quadratic equation. In other words, we want hunting for 1, we found 2, which is good, actually. Then these two solutions have this square root on it. Well, this square root could have one of three possibilities. Either the argument of the square root is positive, in which case this whole number is real, in which case, in this case, then you'll have two possibilities. So either with a minus or with a plus. Both cases are negative, as a matter of fact. Both cases are less than 0, because this is obviously a less than 0. This one is 2 less than 0 because you have lambda and you have lambda squared. Let me throw in some numbers in here, okay, just to have a sense of what these things are. A typical value for the inductance is L. Can I write it in a different color? I don't want to write it in the same color because that was from the last lesson, okay? So I want to mix some numbers in here. So let me get it in red, okay? So L is about 470 millihenry or 0.7 Henry, okay? This is a value. Typical value for capacitance that we saw is about, as a matter of fact, let me use this value. This is 22 microfarads, okay? Now let me use 22 microfarads in here. In other words, it's 22 times 10 to the negative 6 farads. And the resistance, let me take 100 ohms, which is a typical value for a resistance, okay? I built a circuit with these characteristics. Now, that's not going to work. So I need to have a much, much bigger for this case, okay? So I'm going to actually bring a 10 kilo ohm or 10 to the power 4 ohm, okay? I have to have a huge resistance because we are in the case where we are overly damped. So I have to have that, okay? So let's find lambda. Lambda, if you guys remember, is R over 2L. R is 10 to the power 4 over 2L, which is 2 times 0.47. So if I throw in the numbers in here, it's going to be a huge number. So let's find what R is. What lambda is. So it's going to be 10 to the power 4 divided by, open parentheses, 2 times 0.47. Those parentheses. So it's 10,600 and let me write 10,600 radians per second, or 1 over second. Remember, the units for it is 1 over second. So this is the value for lambda. How about omega naught? Omega naught is easy to find from here. And let's see if we can find the, it's 1 over square root of LC. And square root of LC is 1 over square root of 0.47 times 10 to the power times 22 first, times 10 to the power negative 6. So let me put the numbers in here, times 22. So I'm going to put it in the calculator, and hopefully you're doing the same. So what you have in here, you have 1 over square root of, open parentheses, 0.47 times 22 times 10 to the negative 6. It's going to be a big number, but it should not be as big. So it's giving me 311, basically, 1 over seconds, also the same unit. Obviously, in this case, lambda is bigger by a huge factor than this number. So if I plug in the numbers in here and try to find this root, so the alpha 1 is going to be negative lambda, negative square root of lambda squared minus omega naught squared. So if I plug in these numbers, and alpha 2 is the same thing, except that it has lambda squared plus in here, and in here it's the same thing. So I need to take the square root, I need to take negative lambda, which is this number, plus the square root of, open parentheses, of this number squared now, which is lambda squared, minus omega naught squared. It's going to be very close from lambda, okay? Because it's a negative value, which is important. That's my whole point in here. So this is a negative value. Oh man, it's not that big. Okay, yeah, because the two values are very close from one another. So when you subtract them, the point being in here, it's a negative value, negative 4.55, 1 over second. Okay, how about this number? That's going to be a huge number. So I'm going to take the same expression and change the plus to a minus. So it's negative 21,200, basically. 21,300. Negative 22,300, 1 over seconds, 2. What is this notification? I need to go to that meeting. Anyway, so both of them are negative. That is my point in here. So the fact that you have an exponential of alpha 1 or an exponential of alpha 2, both of them are negative. And in this case, the solution will decay, will go to 0 rapidly in either case. The slowest is going to go with this number. Okay? But that's still very fast. So it's going to go to 0. And that's what you want from your shock absorbers, by the way, from your car. You have 4 of them in suspension. When the car hits a bump, you don't want it to continue oscillating. You don't want that. You want it to immediately continue smoothly, as if you didn't hit anything. You wouldn't notice it. So that's a good suspension system for a car. Bad suspension system is when your lambda is not big enough and the car starts to show oscillations. You don't want that, because those oscillations can damage the car and can actually loosen a lot of things in it, and then the car does not last as long. So if you see that in a car, that is a sign, bad sign. Now the second one is in case when both of them are equal to 0 to one another, and it can cook R so that it's equal to the other one. So I need lambda equal to omega naught. So I need, for this case, lambda equals to omega naught. And I know lambda is R over 2L. And this one is 1 over square root of LC. So that means that R that makes this happen is 4L, because I square it, divided by C. So what is the R, the critical value that makes this thing happen for me? I have to find it, and it's a square root of, open parentheses, 4 times L is 0.47 divided by, open parentheses, is I want to make sure I have multiplication symbol in there. It's 22 times 10 to the negative 6. And it's 292 ohms. Okay. If you have any resistance higher than this, I took a big value in here, which was 10,000. If I took 300 also, it's going to give me negative numbers in here. So if I change this number in here to 300 only, it should give me both lambda and both alphas negative. So even if I choose R equals to 300 ohms, it should make this number small enough, but it's going to make the whole thing positive, negative numbers. So let me go back into the math and find the value that I have in there. So I'm changing 10,000 to just 300. Okay. So I'm getting an R value of, lambda value of 319 or 320, 319.1. Okay, so it's 319. So this is lambda. I'm going to find lambda squared under the square root. Let me find both alphas in here and change the value that I have in there. So I have a negative, this number, minus, open parentheses, square root first, of open parentheses, this number squared, which is lambda squared, minus omega naught squared. Omega naught did not change, so it's still whatever value that we had before, which was 311. So that did not change at all. Squared, close the parentheses, and hit enter. So it's a negative number. It's a negative 390 actually. So that is alpha 1. So alpha 1 is a negative 390.87 to be more specific. And let me find alpha 2, which should not be too far away from it too. But both of them should be negative. That's the whole point of this, negative 247. So both of them are negative, even for when R is 300 ohms. You don't need to have 10,000 ohms like I did, killing it big time. Even 300 ohms will kill the current in this case. So let's try. So if this number now is not that, is not any of these two numbers. By the way, I don't know if I shared with you the screen in here. This is, let me stop sharing that screen and share with you what I did the calculations in here. So this is where the calculations are showing. This is the last value of alpha 2. This is alpha 1. This is with a positive and this is with a negative. Both of them are negative. That's the whole point of the calculation. Okay. because R is more than that critical value of 292, okay? Because even in this case, I changed R to 300 divided by 2 times 0.47, because R over 2L. So that gives me the value of lambda. The first cases were too much. They were too big numbers, okay? So I hope that you guys have calculators and you're checking this thing. So you're checking it with me. So the point being in here is there is a critical value that makes that happen, and that is the formula for it. So this is the critical damping. It's still, both values are, and then in this case, you'll have the square root is 0, but you still have this value, exponential and negative lambda, that will kill the behavior. So it's still also damped, but not as fast. As a matter of solution is some polynomial in the first order of time times the exponential, in this case is going to decay. The case that is of interest to me is the case when lambda is this one. Namely, let's choose an R that is smaller. Let's say, for example, 100 ohms, okay? If R is 100 ohms with the same data for L and C, R is 100 ohms, then in this case, R over 2L, which is lambda, by the way, is going to be equal to 100 divided by 2 times 0.47. If I plug in that in the calculator, that should be less than omega naught. Omega naught, remember, it's still that value of, what is 310.9 or 311? Okay, so this should be less than 311, which makes it the case that we're studying right now. So if I plug in the numbers in the calculator, so we will have 100 divided by, open parentheses, 2 times 0.47, and close the parentheses, and the answer is only 106.3. So it's 106 1/2. Obviously, this number for lambda is less than the value of omega naught. Omega naught did not change at all. I didn't play with it, so it's still this number. So 311 is more than 106. Therefore, the square root is not positive anymore. The under square root is not positive. So the number is a complex number. It has an I in it. Using Euler formula, then this suggests that the solution, which we wanted, actually exponential of exponential alpha t, has a value in it that is not real, that is an imaginary. As a matter of fact, the solution will have, let me now go back in black. So the solution will have an exponential of I times I, I'm sorry, there is no I first. It's alpha, and alpha, remember, has a minus lambda plus or minus I. The square root now, if I rearrange them, it's going to be positive times t. This is the oscillating part. This is the oscillation, namely cosine and sine, according to Euler's formula, this one. And this is the part that is damped. So the solution should look like this. Q sub t then will be, in general, a constant, A, times an exponential of negative lambda t, times a cosine of this number, omega naught squared minus lambda squared, times t, plus some initial phase. So this is the general solution. Let me explain each term. The phase phi and the amplitude A depend on the initial conditions. Namely, how much current did we have and how much charge did we have in the circuit, okay? Condition, same thing with the initial conditions. And this is going to be the actual frequency, or the angular frequency to be more specific, of the system. So to go back into my data, the numbers that I throw in, remember, I have R equals to 100 ohms. So R in this case, and we have L equals to 22, I'm sorry, that's C actually, 22 microfarads, or 22 10 to the negative 6 farads. And I took L to be 0.47 Henry, or 470 millihenry, which is a typical number, okay? So I just took these numbers now. We have a lambda that is equal to 106 or 1/2, the unit for it. And we have an omega naught that I can calculate now. Omega naught I mean, the square root, I'm going to call this whole thing omega, because this whole thing is just the coefficient of time in this expression. And the coefficient of time is the angular frequency. So the angular frequency of this circuit now is omega naught squared minus lambda squared. So empowered with that, so I'm going to take the square root of, open parentheses, omega naught squared is 320. No, actually it's 310.98. So I'm going to square this number and subtract from it lambda squared. Lambda squared was 106. I found it last time. Yeah, 106 squared. And close the parentheses and then the square root. And this is the number now that we're finding. Actually, we're finding this frequency to be 292 1/2, but because it's an angular frequency, we usually refer to 1 as being radius, because it's now measuring angles, because it's measuring this angle, okay? The argument of the cosine is always an angle. So that is basically why we changed the unit now to radians/second. So this is the angular frequency of the actual system. So let me plot this function for you guys to see how it looks like, okay? So I'm going to stop sharing the screen, and I'm going to share with you this calculator. And let me move it in here. So I'm going to go to the graphing capability of this calculator. And I'm going to enter my function. Function y equals to, I'm going to leave the amplitude in here 1, okay? Because we can always divide by the amplitude. So I have an exponential of negative number in there. So I'm going to put it in negative. So I'm going to write it as a lambda, okay? So I'm going to write it as an L, if you wish, okay? So I have an L in here times t times x. Or let's put it in terms of x, because this program recognizes x as the independent variable and y as a dependent variable, times the cosine of, I need to have a value for omega naught. So I'm going to put a value in there, which is the square root of, open parentheses. So I'm going to put in here, to control this parameter lambda, as just, let's put 4 in here, okay? Minus L squared. Okay? And this whole thing is part of the times x, okay? And this whole thing, close the parentheses, and let's enter this function. So I chose the phase phi to be 0, okay? And this is the function now, how it looks like. So obviously I have to take care of this exponential in here. Why did I put it in here? Let me get rid of this extra x in here, put it in terms of the, and let me make sure that I'm doing multiplication in here, so that there is no epsilon. Okay, that's how it likes it. Okay, so now let me make sure that the function that we're using, radians. Okay, radians is fine. Okay, so let me go to the graphing again in here, and let's see if I graph this function in here. And of course, I want to graph it from 0, because time does not change in the we don't care about time in the past. So let me go to graphing range. Now graphing range, plotting range, and start from 0 actually in the x-axis. Since I know the maximum value in the y direction is going to be starting from, so let's make it -1 to +1, 1.5, 1.2. And let's plot this one. We know pi is 6.28. So if I wait for like 2 pi, so I need to wait for about 15 seconds, basically, okay? So this is how the function look like. Obviously, this depends on the parameter L. As you can clearly see, L is between 0 and 2. So let me make this L bigger than that. It's gonna be a problem, because it's gonna be an imaginary number, and here square root of an imaginary number doesn't exist. So L cannot be greater than 2. That's why the program is restricting it. But I'm going to make the lower limits smaller, okay? So I'm going to make it 0.01, okay? And change the value of R. Where is my mouse? Change the value of R. As you can clearly see, the more I have of this, the less lambda, the more oscillations I have. The more lambda, the more damping I have. So let me make this graph look a little bigger and change the plotting range instead of 15 and here to about 45, okay, to see what's going on. So it's still damped, even with this low resistance. Remember, lambda is a measure of R over 2L. And I took the frequency to be, actually, omega naught to be 4 in this case, okay? Omega naught to be 2, so when I square it, it's going to be 4. So that is basically how the system is behaving in here. This thing that you see in here is the envelope. And it's ultimately going to stop. So there is an oscillation with damping in here, as you can clearly see. There is an oscillation, and the frequency of the oscillation is this parameter, actually, square root of 4 minus L squared. If I change L, the frequency will become less, okay? So in other words, I'm changing L now until at some point, basically, practically it goes away at 2. So there is no frequency in here, but there is this exponential decay, okay? Because then if I make it bigger, it's going to be a negative number, okay? So technically, I can find another function in here that I really need to plot. And that function is for L greater than 0, and then plot that one in there, okay? So there will be no oscillations, but condition for it is L greater than 0, it should take over. But the point being in here, this is good enough for the illustration here of this graph. So, oh man, it went back to the same range that it was before. So let me go back into 0. Let me make this one 60, okay? And let me make this one -1. And let me make this one 1.1, just enough to see the oscillations. So again, this value of 1, so if I decrease the damping, there will be more and more oscillations. And that's a disaster thing if you do that. So if it's 0, there is no damping. So it's oscillation forever and ever. Because if L is 0, exponential of 0 is 1, and square root of 4 is 2, so it's 2x. So it's a completely bad suspension system on your car. But as the R starts to increase, in this case, there is more and more damping, meaning that the resistance is wasting all of the energy, or a lot of the energy, more and more of the energy in terms of heat. There is oscillation between the inductor and the capacitor, but the resistor now has more and more say on that energy. It's wasting it, basically, and that's why you see this exponential decay. Now, if you increase the resistance, the value of lambda is going to be more drastic in a sense. At the end, you have hardly one frequency because it's maxed, went to the opposite side, now it's maxed again. So we have one full wavelength, one full period, I'm sorry. And then the next period, you hardly can see it. You say, oh, it's gone. No, it's not, because I can zoom in on the y-axis and you will see it there. So let me go to the plotting range and change the y-axis from -0.1, for example, to +0.1. And you will see that you still have oscillations extending for a long time. As a matter of fact, what you thought was damped, there is still another period that showed up. If I go to the plotting range and now make even this one smaller, you see that this range is actually extended beyond that. So it never really equal to 0, okay? Because you see now, there is more oscillations. Remember, the first one has this peak now, which you can see because we're so zooming in on this. And now we have clearly the second peak, and the third one starts to appear. As a matter of fact, I can go to the plotting range and make it extremely small and see more and more values in here. Okay, so the other two are completely gone now because they're completely out of range. And now I see more and more frequencies that extend to almost 16 seconds. Okay, if I go back to the normal range, you hardly see any oscillation. So right now it's giving me that. So I'm going to go from -1 to -1.1 to +1.1, the original one, and you see that the oscillations seem to have died out immediately after what? This is 16 seconds, this is 12, this is 8, this is 4 seconds, a little over after 4 seconds they died out. Okay, so that is basically what this whole thing is. Does this make sense to you guys?
Yes, it makes sense to me.
Okay, very good. So I'm going to stop sharing the screen. I'm going to go back into the math, the theory, and share. So this is a very, very important circuit. The Rlc circuit is extremely important, okay? And now we have an understanding of how this thing works in terms of behavior. This is called actually transient behavior. This is exactly what happened when you try to unplug a device from the power supply and you see that spark, or you plug something and you see spark. This is actually transient behavior. Usually the transient behavior does not last long because of this exponential that you see in there, okay? So it's going to decay immediately. But it could be very intense in any circuit. It could actually cause a lot of damage, like the spark you see. So it could damage your circuit. So usually you have all kinds, that's why you need the resistors in the circuit actually to kill those transients. And then you have your steady state current. So chapter 31 actually is the next topic in here. So I'm going to jump into it. And now we're going to have the same RLC circuit, except in the following configuration. So let me show you how this looks like. So we have a resistor. You have an inductor. And you have a capacitor. Except now you have a power supply that is alternating. So how are we going to make an alternating power supply, you ask? Okay, let me show you how. You have a switch. So the first thing we need to introduce in here, so this is the RLC circuit. With an AC power supply, like the wall. So let me see how we can make one. Remember when we had Faraday's law, we said the following. If I have a magnet in here, let's say, for example, this is the north pole of the magnet, okay? And there is another magnet in there in the opposite direction, basically facing it, where this is actually the south pole, okay? So there are magnetic fields in here that are pointing in this direction. So this is the B field. So these are two permanent magnets, and the red that you see in here is the B field, the vector B, okay? Between that region at least. So what I'm going to do in that region, I'm going to bring a wire. Obviously, a wire will not cut it. You have to have a bunch of wires wrapped around, okay, to make it work. Otherwise, you're going to generate hardly any power. So you have a wire that is made up into this shape. And that spins in this region. So think about it this way. The way that you construct this wire is by having what is the motor? It's the opposite of a motor, really. Where these things in here are the so-called brushes, okay? There is a gap in here. As this one spins, there is a gap in here. These are where the brushes are. Where are they? Here, on this side, okay? Here. There is a gap in this wire in here that sometimes, so I'm gonna draw the brush in here. Let me draw it with a different color, because it's getting crowded in here. So there is one side to the brush, and there is the other side to the brush, okay? And it's connected to something in there, like a resistor, for example. Okay, so this is what's going on. As this spins, sometimes this leg of this circuit is in contact with this brush, this side of the brush. Then when it spins, because of the gap, it loses contact with this one and enters in contact with the second one. The other one at the same time enters contact with the second one. So there will be always contact with the brushes in here, no matter which way you do it. However, the area that you see in here of this loop is A. And it's pointing in this direction. So this is the area A. And it's a fixed area. So area in magnitude is not changing. So the loop, you don't change it. The B field, you don't change it. Both of them, you don't change them. But what you do in this case, you're spinning your loop by an angle, by a rate omega. So this angle now is changing at the rate of omega. In other words, the angle itself is omega t with time. Having said that, then I can do the dot product of these two vectors, B and A, to find the flux of the magnetic field. The flux of the magnetic field will be simply equal to the B field times the area. because you don't need to integrate over any area. The area is fixed, so there is no integration in here. The only thing that changes in this case is the angle between them. I'm going to write it to omega t, cosine of omega t, because the flux is changing with time. That's all that matters in terms of Faraday's law. You will have an EMF, so there will be an EMF in here. There will be an epsilon in here, and that EMF is given by Faraday's law that says the derivative of the flux with respect to time is your EMF in absolute value. So if you take the derivative of this one, B is not changing with time. The area A is not changing with time, but the derivative of the cosine is definitely changing with time. So when you take its derivative, you pull an omega out of it, and the cosine becomes a negative sign, which cancels that negative and becomes a positive. So it's a sine of omega t. So in actuality, what you did, you have created a current that changes with time at a regular rate. As a matter of fact, if I want to plot this function, this is how this function looks like. This is some epsilon naught. So this is a maximum value of the voltage. So let me write it as Vmax instead of epsilon naught. So this is some maximum voltage. And then this one alternates between a positive and negative value. So this is how this looks like. So the sine function is a periodic function, and the periodicity in this case is equal to 2 pi over omega. So t is 2 pi over omega, which is equal to 1 over frequency, okay, of the signal. So this is how the sine function look like. It starts from 0, goes to a maximum, then come back, and the cycle repeats after that. So it's going to be a cyclic operation where this cycle comes back and so on and so forth, okay? So the point being in here is that this is the Vmax. This is the maximum voltage in here that I was talking about in here. And this is the negative Vmax. So it's always changing between Vmax and negative Vmax. And it's a sine function. I wrote it as a sine function, but don't get confused by the fact that it could very well be a cosine function. If I shift my time in here, and so that there is a 90-degree delay or before, in other words, don't look at the clock until later, okay? So in this case, there will be a 90-degree angle, actually a negative 90 degrees. So let's delay it in the opposite direction. So cosine of any angle minus 90 degrees is actually a sine of function. So it could end up with cosine of omega t minus 90 degrees is actually a positive sine of omega t. That's a trig identity because cos of alpha minus pi over 2 is actually cos, which is 0, plus sin, and sin of pi 2 over 2 is 1. So it's actually sin of alpha. So this is a trig identity that helps us see that. In other words, this is what you're saying, okay? What we're saying in here is 90 degrees is a quarter, basically a cycle. So if you shift the graph in here by quarter cycle, by quarter period, this whole distance is a p. Is t. So this distance is t, and this distance is only fourth of that, t over 4. If you move the axis in here, the graph is actually that of a cosine function. So the graph with this will become a period t, which is the same period as before. Okay. So this period was measuring from 0 to 0. This one is from max to max of the sine, or from the max to max of the cosine too. Okay, so that's the same period t. It's the same value. It's omega over a 2 pi over omega. So it's the same value as far as the signal is there. So the fact that I wrote a cosine in here, please do not get confused with that. It's just a matter of choosing the origin of time. It's a matter of just choosing when to hit the start button on your time device. Okay, just shift it to the left and the cosine becomes a sine, or the sine becomes a cosine. It's both of them are identical graphically and also algebraically too through this expression. If you're curious trying to see what happened, just look at sine of alpha plus of pi over 2. Sine of alpha times cosine of pi over 2, that's 0. Cosine of alpha times sine of pi over 2, that is actually cosine of alpha. It's the same identity actually written backward. That's all. Okay. In other words, one negative and the other one positive, and everybody's happy. So this is actually how you'd make current into an AC current. So now in this circuit that I started with, so imagine with me, I have a Vmax of some sort. And I have an omega in this case of the signal, which I'm going to call omega prime. Let me tell you why I'm calling it omega prime. Just because I have a bunch of omegas, I really need to keep tab of in this circuit. The first obvious omega is a natural frequency, omega naught. So when you're dealing with an RLC circuit, you have to keep tab of all of your basically time characteristics. Lambda, which is R over 2L, and then you have an omega naught, which is 1 over square root of LC. That played a major role in our calculations before. And then there is another omega, which is the actual frequency with which the system actually oscillates, which is square root of omega naught squared minus lambda squared. And if you're curious trying to find what lambda is, it's just R over 2L. So these are two frequencies. On top of that, now we brought another omega to the mix, which is coming from the circuit, from the power supply. So we're going to call this one omega prime. This is the power supply frequency. And I use the word frequency loosely, and that is how physicists actually refer to it. We mean, if it is an argument of an angle, the angular frequency. If not, refer to this expression between them. The actual frequency and the angular frequency are related by 2 pi. Basically, just 2 pi is the one with them. So the word frequency in here is just refer to the same quantity. I mean, just divide by 6.28 or multiply by 6.28 to find one or the other. Okay. So you have to keep tab of your time characteristics. One of them is lambda, which is easy because that is actually the effects of the resistance. Now you have 3 more omegas you have to keep tab of. There is a natural frequency, which is this one. This is the natural frequency. Okay. There is this one, which is the actual frequency. Okay. And there is this one, the driving frequency. But this is the actual frequency of what? This is not any frequency. It's actually of the transient that I was talking about earlier. And this is actually the one that just came in, the third one now, frequency. I'm going to call it omega prime. So if I call it omega prime, please make sure that you change this symbol to T prime. In other words, T prime is equal to 2 pi over omega prime, and T is actually 2 pi over omega, and T naught is actually equal to 2 pi over omega naught. So everybody now gets a new wardrobe, if you wish. Okay, new clothes. Okay, so this is 2 pi f prime. This is the driving force, frequency. This is 2 pi f. This is the transient frequency. And this is actually 2 pi f naught, which is the frequency of this power source. As a matter of fact, in the United States, we know exactly what f naught is. F naught in the United States is 60 hertz. I'm sorry, did I call it f naught? F prime, F prime. What am I talking about? The F prime. This is the power supply. This is the transient, and this is actually the natural frequency. The natural frequency depends on your L and C. Natural frequency depends on how much L and C you have made up your circuit. This one depends on actually the difference between these two numbers. This one depends on the power company. In the United States, F prime actually, let me fix that. F prime, which is in the US, this is US, not, okay. This is equal to 60 hertz. That's how much in the United States. In the rest of the world, basically F prime is 50 hertz. Okay, that is the power company that determines this number for you. In other words, omega prime in the US is 2 pi f prime, which is 120 times pi, radians per second. Okay. In other words, we know these values. I mean, 120 pi is what? 3 point something times 100, so it's about 400 radians per second. Okay. So these numbers are known. In the rest of the world, it's going to be 100 pi or 328 radians per second. Okay. So that is some of the numbers that we know up front. Okay. Unless you have a different power supply, and in the lab we do, in a sense, we can change the frequency of the power supply if we're doing lab. So we can control that number too. And if you are broadcasting company, you change your signal because you have this company that changes this sends this signal, another company sends another signal, another broadcast company that sends another signal. You don't want them all to be in the same frequency, because if they are all in the same frequency, which one are you going to listen to? They will all be following the same frequency, and you cannot pick up one over the other. So FCC actually regulates which frequency each operator has a right to. So they issue a permit, and this is your frequency of operation. So if you go to your radio or your station and your device, you can tune it to a specific frequency, and that is how you get into the signal of that specific station. So again, F prime can be controlled, okay? Can be controlled. But for a regular power wall jack, it's actually fixed to 60 hertz, at least for the most part, okay? Unless you have specific applications where you need it, like in a laboratory environment, then you can play around with this number. Okay. So this is basically in terms of the power supply and the fact that now we have 3 or 4 time characteristics that appeared in the circuit. So let me write Kirchhoff's rule in this case. When at t equal to 0, when we close the circuit, I'm going to assume there was no charges in the circuit and the current was equal to 0 in the circuit. But in here, the power supply will send a current. It could send it this way in one cycle, and the next cycle it's going to send it in the opposite direction. So it's going to send it according to its own frequency, F prime. Okay? In 1 second, 60 times basically is going this way. I mean, 30 times is going this way, and the other 30 times going in the opposite direction. Oh, what am I? No, there are 60 times going up this way and 60 times in the opposite direction. Change it 60 times at once. 60 times is like this. So 60 times is positive and 60 times is negative. Okay? It's changing it all the time. So when you look at the plug in there, the polarity on those ends is changing. Sometimes one of them is positive, the other one is negative, and they do that 60 times every second. Okay? That's what this whole thing means. So we're going to catch it in one direction. We're going to catch it when it's going clockwise, okay? Then write Kirchhoff's rule now. So we know the voltage drop across a resistor is Ri. That is easy. The voltage drop across the inductor is LdI over dt. The voltage drop across a capacitor is Q over C. And at this point, the voltage is actually rising in this direction because that's where this power supply is pushing it this way. When it sends the current in the opposite direction, everything changes sign, that's all. So we're going to take a point in here, and we're going to go back and come back to it. So in this case, we drop by an Ri, we drop by an LdI over dt, we drop by Q over C, and then we rise by this voltage that I just wrote, okay? Except I don't like the sign, I'm going to call it a cosine, okay? So here is the deal. So across a resistor, it's Ri. Across the inductor, it's LdI over dt. Across the capacitor, it's Q over C. And now on the other side, I'm going to write it as Vmax cosine of omega prime t. That's all. Okay? Here is the problem with this equation. It's still a complicated equation. Remember, I is the rate at which the charge is changing with time. That means di over dt is my second derivative of q with respect to time. Okay? So these terms in here, I have them in that equation. So I can rewrite the equation as follows. First of all, L, the second derivative of q with respect to time, plus R, the derivative of q with respect to time, plus q over C equals to Vmax. And then I have to have that cosine of omega prime t. I can divide by L if you wish and rewrite the expression in terms of my known parameters, which is 2 lambda times dq over dt plus omega naught squared q is equal to Vmax over L, because I divided by L, times cosine of omega prime t. Okay. Now this equation is very hard to do. Here is what the math tells us, okay? And it's beyond the scope of this class to really try to understand how this thing works, okay? But let me tell you the physics of it. You have 2 solutions. A transient solution And transient solution is the one in either of the three cases decays like exponential negative lambda over lambda t. Whether case of overly damped, R is very large compared to the square root of 4L over C, or R equals to L for square root of 4L over C, or R less than square root of 4L over C. In all of these three cases, there is an exponential. In here, it's very big. And in here, it's there, and it's dominating. And in here, it's there, and ultimately it's going to win. Although there will be oscillations, but ultimately it's going to kill your solution. So that's why it's transient. And it's transient because of this behavior. So it's ultimately, it will decay. So this solution is really, depends only on the initial conditions, including the fact that you just turned on your circuit. Because the fact that you turned on your circuit right now, it's equal to 0. When you close the switch, this is S, okay? So S is closed at that point, at equal to 0, closed, not 0. So in that situation, what's going on in here is there was no charge in the capacitor. There was no current in the inductor. So there was no initial energy in the circuit, but there is this thing that kicks things on. And that will trigger immediately this transient behavior. But it's going, the good news about it, it's going to ultimately to go to 0. So this solution is really not interesting. It doesn't mean it cannot be damaging. As I said before, it could have tremendous effects on your circuit. So never forget about the transient, but it doesn't last too long, that's all. So after that, what happened is there is the steady state. So this is solution number 1. And solution number 2 is the steady state. That is the one of interest to us, the steady state. Let me talk about why this is steady state solution. In math, they don't call it most of the time steady state. They call it the special solution, okay? Steady state solution. Let me talk to you a little into where is this coming from in the physics in here. The fact that you have a voltage Vmax in here turned on at equal to 0 with a frequency omega prime. This voltage will stay all the time. It doesn't depend on the exponential of negative lambda or t. It's going to remain with the circuit. So this effect will stay long. So we expect the following. We expect the steady state to depend on two parameters, Vmax and omega prime. So this solution must depend on Vmax and omega prime. As a matter of fact, we know. Obviously, if I play around, monkey around the frequency, there will be a steady state all the time. So that is not a problem. The problem is Vmax itself. If you unplug the device from the wall, there should be no current after it. There might be a transient, and the transient will die, but the effects of the steady state should go away because there is no steady state if I don't have it plugged. So expect the intensity of the current, which is Imax, to depend immediately on Vmax, to be proportional to Vmax. In other words, the current that I suspect will be oscillating, and it has to, because it needs to depend on the frequency omega prime, need to be proportional to Vmax. In other words, if somehow we're going to cut the wire or unplug it or turn off the whole power supply from outside, or the power company run out of energy, I know that what should happen is that Imax should be killed immediately, okay? Then there is the transient again, because the transient happen on both ends when you turn on your circuit and when you turn off your circuit. There is always that nagging thing in there, and that's why there is warning on all of the electronic devices. Be mindful of the fact that don't put your hand immediately after you unplug the device, because there is that transient that did not get killed completely. Because guess what? The inductor still has current in it, still has energy in it that's trying to push it. The capacitor still has charge in it that's trying to get rid of it. So if you cut the power immediately and you put your hand on the device, the transient now is working. And it could cause severe damages. So the mere fact that you killed the source of the steady state does not mean that there is no current. That is the other one. In other words, there are two solutions to the problem, mathematically and also physically. So there is that transient solution that appears immediately after the circuit is turned on, but then dies out and then reappears again, because at that point there is still current before you kill the current. And there is still charge in the capacitor. So the mere fact that you just killed it, so now the capacitor has energy. It wants to get rid of it through the resistor. Same thing with the capacitor. It has energy. It wants to get rid of it through the resistor. Both L and C, they want to get rid of their excessive energy. One of them in the form of current, the other one in the form of charge. And they need time. The bigger, of course, R is, the bigger lambda is. Since lambda is big enough, the bigger this effect is. So you would want to immediately dispose of it if you want to. Sometimes you can't, because you cannot really have too much R in it. So sometimes you still have finite value of R, which makes lambda small, which makes this effect take longer than expected. Okay. So in this situation, you're stuck. You have to wait for it to do its trick. You have to give the resistance time to kill the current. But in any case, the current in the circuit in the steady state must be proportional to Vmax. This is a requirement. We cannot play with that. This is actually required. As a matter of fact, I'm going to see how this equation looks like if I require, so this is what I want. I require, because look at this circuit in here. Look at this equation in here. This equation in here, that's fine. Here it's fine. Whichever one you look at it. This one, this is coming directly from Kirchhoff's rules. Or this one when we divided by L and rearranged it, that's all. This is what I'm saying in here. Either one, look at it. Q is here. So that's Q. The derivative of I, which is actually a Q. Because if Q is some cosine function, so I'm going to say that Q is somehow a cosine function of the same driving frequency in here, may be shifted, okay? May take effect a little later because of that transient in basically pausing the effect of the steady state. So it may be shifted a little, but there is a frequency omega prime. So it needs to be in tune with the steady state because the steady state is the one that caused it. So there is that one in there. Then it must also be proportional to Vmax too. Now, if I take the derivative of this one to find the current, the derivative of a cosine is going to be a sine, and it's going to be an omega prime times t plus phi times some omega prime and times the rest everything. But the main thing in here is the Vmax times Q. I mean, this is I. And the derivative of I with respect to time, when you take the derivative of the sine, you're going to end up back into the cosine, and there is another omega prime that will be pulled up and everything. What interests me in this analysis is the fact that there is actually a Vmax in that too. So there must be a Vmax in here. There must be a Vmax in here. There must be a Vmax in here to cancel this Vmax. That is important. Okay? Otherwise, this equation, because we're looking for a special solution, we're looking for the steady state that needs to be proportional to the external cause of this whole thing, and that is the external power supply. So if this power supply is somehow ended, then this whole solution should not exist. Then you're back into just the steady, the transient. Okay, so that is basically this whole argument in here. Now, the fact that I'm saying there is a phase shift is because the combination of a cosine and a sine does not necessarily give you this cosine prime. So you really need to shift the values in here so that at the end you will get that cosine prime, cosine of omega prime t. Okay, that's why you really need to shift these values a little so that you play with that phase, so that at the end the cosines and the sines and everything will amount to this voltage. So that is how the whole argument is. So let's take a current now, since I know the charge is going to be some cosine. I'm going to take a current, which is the derivative of cosine is going to be a sine. So I'm going to make the current look like lowercase I, because we need to find the time-dependent current. So the current as a function of time to be simply some maximum value, which I don't know, but I expect to be proportional to Vmax, times the sine of omega prime t plus some phase, okay? That is the whole thing, okay? I want to find the solution in here. I'm hunting for it, okay? So if I do that, then I know how to integrate this expression to find. So immediately, first of all, the voltage across the resistor is simply Ri. So 2 is going to be Ri max times that same sign stuff, okay? Correct? Now, if I want to find the voltage across the inductor, that is simply L times di over dt. And the derivative of a sine is just a cosine. But don't forget, you have an omega prime multiplying t, so you have to do the chain rule. Once you do the chain rule, this will become omega prime times L times I max times a cosine of omega prime t plus phi. Okay? So I'm going to go back into my expression here that I made a long time ago about the trig identities and things like that. I ended up with a cosine. I really wanted to be a sine. So what I'm going to do is add to the argument 90 degrees and write it as a sine. Because of the fact that I took the current to be sine, so this voltage across the inductor, the resistor, is actually the same sign as that of the current, because just multiply by R. In here, because I took the derivative, the sign became a cosine. So I can write, it's very important that you know that this is actually not a requirement, but it's coming from the stemming from the fact that I need to compare apples to apples. So I'm going to make omega prime L times A max times a sine now. I don't like this cosine, in other words. I wanted to write it as a sine, similar to everybody else. Omega prime t plus phi plus 90 degrees, or pi over 2. Okay, if I do that, then I have a cosine, because the sine of this argument times the cosine of pi over 2 is 0. Cosine of this argument times sine of 90 degrees is 1. So we actually have that. This is a trig identity, okay? So now this looks similar to the voltage across the resistor. This looks similar to the current, with the exception, I mean, this value changed things a little, but the angular value has changed by 90 degrees. So what I'm going to say is the following. The voltage across the inductor is 90 degrees ahead of the current, because the current has a sine of omega prime t plus phi plus some phase, which I don't know what it is, but we should be able to find it later on. And I max, which I don't know what it is, but we should be able to find it. We know I max need to be proportional to V max. That's all. That is what we're requiring, but we have no idea what it is equal to. We should be able to find it. Okay. Now, this is what the current look like. This is what VL look like. So they're out of phase, and the phase is 90 degrees. As a matter of fact, it's plus 90 degrees. So the voltage across the inductor is 90 degrees ahead of the current. As a matter of fact, I can make an assertion in here, because the VR has a sine of omega prime t plus phi, and the I has a sine of omega t plus phi. So both of them have the same phase. There is no 90 degrees or 7 degrees or any degrees between them. Actually, they're in phase. So in this case, they're in sync. Actually, the voltage across the resistor, is in sync with the current. They're together, running together, same time. Okay, good. How about the capacitor? The capacitor, the voltage across it, if you guys remember, V across the capacitor is Q over C. And Q is the integral of the current. So this is the integral of I sub t dt. And the integral of I sub t dt, first of all, I have the I max that needs to come out. And then I have to integrate the sine. The integral of a sine is 1 over omega prime. And it's going to be a negative cosine. So it's going to be a negative 1 over omega prime c times a cosine, because the integral of a sine is a negative cosine, omega prime t plus phi. I don't like this business of cosine again for the same reasons that I raised the objections on VL. I'm going to do the same thing for VC, but I have this negative sign also in addition to it. So I want the minus cosine to become a positive sign. So for me to do that, I'm going to use the other trig identity that we saw today. Did we see it? No. It's actually easy to see. Sine of alpha minus pi over 2 is the same as cosine of alpha. Let's see why. Sine cosine is 0 minus cosine sine, and so this is actually a minus sign in here, okay? So this is exactly what I need. I have a minus cosine, so I want it to be a sine with a positive sign. So in this case, VC will be equal positive. It's very important to write it as a positive, omega prime c times a sine now of omega prime t plus phi minus 90 degrees, okay? So it looks like it's similar, except that instead of positive 90 degrees, I have a negative 90 degrees. So what I'm going to say now is the voltage across the capacitor lags by 90 degrees. Lags, it's behind basically, by 90 degrees compared to the current, Here is the new quantities that appear. Oh, I'm sorry, I have Imax. I forgot about Imax in here. I have Imax in here. Remember, we took the integral of I, and I has an Imax in it. So this is how the situation where what we're looking at. If the current is an Imax sine of some argument in here, it doesn't matter what that is, omega prime t plus phi. The voltage across the resistor is just R times I, which is R times Imax times the same sign of omega prime t plus phi. Now, the voltage across the inductor, VL, is omega prime L times the same current Imax times the sine of omega prime t plus phi plus 90 degrees. And the voltage across the capacitor is actually 1 over omega prime c times Imax times the sine of the same angular frequency minus except pi over 2. So everything seems similar, except that now I'm multiplying the current by a resistor, R. I'm multiplying the current in here by omega prime L. I'm multiplying the current in here by 1 over omega prime C. So the amplitude have changed. In other words, L max is no longer, I mean, it's depends first of all on the frequency, omega prime L times I max. The C max, this is a maximum value, by the way, because the sign can be positive 1 or negative 1 at most. It's 1 over omega prime C times I max. And the VR max, the voltage across the resistor at max, is equal to simply R times I max. Okay? So what I'm going to do in here, I'm going to introduce these vectors now. Okay? Whose length are all of them I max in it, times these quantities. I'm going to introduce a concept called the reactance. So the reactance by definition for the resistor is just R. And the units for this one is in ohms. The reactance for the inductor is just omega prime L. And the units for it are also in ohms. The reactance for the capacitor is 1 over omega prime C, and the units for it too are ohms. So all of these ones are in ohms. So this is basically what characterizes the circuit in here, okay? So each one of them has its own reactance. Each one of them has its own basically current times what appears to be a resistance. Each one of them has its own effect. The problem with these things is both XL and XC depend on the frequency. For high frequency, for omega prime very high, omega prime high, then in this case, it's clear XL is very high, grows higher, and XC goes down because this is dividing by that number. For omega prime going down low, then in this case, XL going low, but XC goes high. So these things change, but in either case, XR does not depend on the frequency. It stays R all the time, okay? So this behavior, we need to take advantage of it. Here's the deal. We still have to introduce the concept of phasors based on this idea, the phasors method. Then we're going to define the impedance of the circuit, and the impedance of the circuit turned out in this case to be equal to the square root of the XR squared plus the difference between XL and XC squared, and this will give me the resistance, if you wish, the effective resistance for the circuit, and it gives me an Imax related to Vmax via this expression. Imax will be simply equal to Vmax divided by Z. So in other words, we found what we were hoping to find, okay? So once we use that method, and then, so this is next time, okay? Because we're running out of time. So next time, and then we will see that they're shifted by a phase that is going to be, its tangent is equal to the ratio of XL minus XC over R, okay? So that we will find everything that we need to do find. So I'm going to stop the recording. We still have about less than 5 minutes. So I'm going to stop the recording right now because there's still a lot of ground to cover in here before we finish this thing. And we'll discuss the resonance in this case, okay? So I'm going to stop sharing the screen. And I will see you guys Thursday, where we continue this discussion. And then hopefully by next week, we will get the, the applications of these ideas, because it doesn't mean anything if we talk and talk and talk and talk, and if we don't throw in numbers and start doing problems and see what it means, resonance frequency equal to the natural frequency, below the natural frequency, and all of that in a real setting, then it will not sync. Do you guys agree on that assessment?
Yeah, it's a lot of stuff to cover, and actually seeing it in action definitely makes a difference for that understanding, that deeper meaning.
Okay. So, okay, very good. So I'll see you guys Thursday. Today is Tuesday, so I cannot see you Tuesday again. So I'll guys see you Thursday, and hopefully we'll have enough. I think we will use down the road, because we will be done with our labs. Also, we'll be using some of our lab sessions for more applications. Okay. So let me stop the recording. Where is the stop recording?